Bologna. 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 So we are looking here at a special case for Kepler's third law, which states that the orbital period squared is equal to some fundamental quantities times the orbital radius or semi-major axis cubed divided by some mass. What we're going to be looking at in this case are special cases known as a geosynchronous and a geostationary orbit. And we tend to use these orbits for satellites. A geosynchronous orbit is such an orbit, and if we kind of break down this word, we see geo, which means Earth, and then sync, kind of like you're in sync with something, not like the band, but just like we're in sync, we know what we're doing. So you're in sync with the Earth. And what an Earth synchronized or a geosynchronous orbit does is it shows up at the same point on Earth or the same spot on Earth at the same time every single day. So at, let's say, 12 midnight, you walked outside your house and you looked up in the night sky and you saw this specific satellite. It would be at that specific location that you see it every single night forever until it, falls out of orbit somehow. Now, while you might be thinking that, okay, in order for that to occur, it needs to have the same period as the Earth's rotation, 24 hours. This isn't exactly true, a 24-hour period. And the reason why it's not a 24-hour period is if we take a kind of picture of the Earth going around the sun, so, here's the sun, and here's the Earth out here with our axis. We might just think, hey, it takes 24 hours for the Earth to rotate around the sun. But the issue is that every day that passes, the Earth is moving its location a little bit, which means that we are actually clipping in to see the sun a little bit differently. We have to factor in how we're rotating while we're moving. And because of this, what really is occurring is we are having the same period as the Earth's rotation, but to appear in the sky at the same point, we need to have the same sidereal day. And a sidereal day is one where you will see the stars in the same position at this point in time. And a sidereal day is just slightly shorter than Earth's actual rotation. A sidereal day is 23 hours, 56 minutes. And some amount of seconds. I can't remember what it is. Doesn't really matter. If you didn't have this sidereal day, then your constellations would never change. We're in the northern hemisphere up here, and where we are, kind of in Pennsylvania, we only get to see Orion's belt at night, kind of during the winter months. If it's July, you're not going to be able to see Orion. You just don't have that opportunity. But during the winter, due to the sidereal day and due to the fact that the constellations move a little bit each day, we're able to do that. And for our satellite to appear at the same spot each day, it needs to have this orbital period. Okay. The nice thing about these geosynchronous orbits is that you can throw them in any direction you want. You could throw them around like this. You could throw them, like that. This one's actually really nice because you can kind of map the entire world as it rotates underneath you, so that's neat. That one's really used a lot by like military satellites. It's tough to get a nice orbit there. But any orbit that you want, you can throw a satellite into a geosynchronous orbit and do that, as long as it's within a sidereal day or at the sidereal day. As for a geostationary orbit is staying over the same spot on the Earth at all times. So if you go out at midnight and you look up at the spot, you'll see the satellite. And if you go out at 5 a.m., the satellite's still in the same spot. And if you go out at high noon, it's still at the same spot forever. And that can only occur pretty much on or just very, very near the equator. And the reason why this is true is if you imagine the Earth rotating, you cannot get a satellite to just orbit up here. That doesn't make any sense. What's it orbiting around? You need to orbit the center of mass of the Earth. So you can't just send one just around the poles like this. If you wanted one up there, to look at a North Pole, then it would have to orbit down like that, right? Oh, that's a little long, but whatever. And that means I can't be looking at this point all the time because at some point I'm looking down at Australia. So we can only really get this to happen at or very near the equator. Okay, but that's our geostationary satellite. It's looking at just one position forever. And these positions are super good for spy satellites because you can look at everything 24 hours with just one satellite. So it's kind of neat there. Now, a geostationary satellite is a geosynchronous satellite because it is looking at the same spot at every point in time. So a geostationary can be a geosynchronous, but a geosynchronous cannot be a geostationary, kind of like one of those old SAT questions. If we wanted to go ahead and calculate the orbital radius of a geostationary satellite or geosynchronous, then remember what we're doing here is just invoking Kepler's third law, that the period squares equals 4 pi squared r cubed over g, fundamental gravitational constant, times the mass of the system, or in our case just really our planet because it's so much larger than our satellites. Now, we need to be careful about the period here. I mean, we're looking for an orbital radius, which is right here. So let's just kind of move things around real quick to kind of solve this out, and then we'll worry about the numbers. So I need to multiply by g and m and divide by 4 and pi squared. So I'm going to get t squared times g times m divided by 4 pi squared. And that's going to leave me with r cubed. Now, if I want to get rid of this cube root here, or I just gave it away. I want to get rid of the cube, I need to take the cube root of each side. And there's two ways to do that. I could write it like this. I can put the 3 on my radical, just like that. I personally don't like to do that. I think it looks nasty. What I like to do is I like to throw these into parentheses. And remember, when you take a root of something, it's really like raising it to a fractional power. This right here is the same as saying a cube root. Okay, so that's how I like to write it. And that will solve us for r here. And that is how we solve our answer. The tricky part to this is while we may know the mass of the Earth as 5.96 or 97 times 10 to the 24th, we know g 6.67 times 10 to the negative 11th, we know 4, we know pi squared. Our period was given in kind of a weird value. Our period was given as 23 hours, 56 minutes. And we don't want either of those units. We need to get this into some number of seconds, which means that we need to do a little bit of a conversion here. There's a million ways that you can convert this. What I like to do, and this is just my preference because this is how I think about things, I like to convert minutes to hours first. And that's going to seem weird. I'll show you how to do it both ways. Might as well. I'm going to show you how to go minutes to hours first and then go hours to seconds because that's just how I think. So what I do is I say, look, I've got 56 minutes, and if I kind of fence post this out, in 1 hour, there's 60 minutes here, right? So that's going to give me like 0.9 something hours. So I get 0.933333 hours, okay? If I add that to the 23 hours I have, that means my period is equal to 23.933333 hours. Now, I know that in an hour there's 60 minutes, and in each minute there's 60 seconds. So that means there's 3,600 seconds, 60 times 60, in 1 hour. This is going to give me some weird, stupid number, but whatever. It's just what it is. 86,160 seconds. Okay? That is the period of our satellite. So if we use 86,160 for our period and then plug in everything else, let's see what we get. At this point, we already have what our solution wants to be up here. It's just a matter of like throwing in numbers, which is arguably the hardest thing to do in this unit. So 86,160 squared times 6.67 times 10 to the negative 11th. Remember, we're using that E button in order to do times 10 on our calculators. This is the mass of the Earth, because we're geostationary, which is 5 point, some people write 9.6, some put 9.7. I'm going to put 9.6 times 10 to the 24th kilograms, divided by the number 4 There's a pi squared. Don't forget the square on that. I forget that square so often and it drives me nuts. I'm like, why is my answer off by about 3 times? And then this is all to the cube root or the 1/3 power. So now, and remember this all equals the orbital radius. Now it's just a matter of like trying not to mess this up on your calculator. I like to go through this step one at a time and then save that cube root for the end because it's on everything. So I like to type in 86160 squared, enter. I get some stupid number here. And then I will multiply that by, just by hitting the multiply button. It says ands for the previous answer, times 6.67 e for the times 10 to the negative 11th, and then I slam enter. Now I've got 0.495. Now I'll multiply that, so times, so ands times 5.96 times 10 to the 24. I get 2.95 times 10 to the 24. I divide by 4, and this is where you got to be careful. Pi squared is like dividing by pi twice. So I like to go divide by pi, divide by pi. I get 7.47 times 10 to the 22nd at this point. And now I need to take a cube root. So what I have left here after just doing all the inside is I've got 7.47, oops, times 10 to the 22nd, and I need to take the cube root of that. On the calculators, the way I like to write this is I like to just put in 7.47 times 10 to the 22nd. I put all that in parentheses, and I throw the caret in like I'm raising it to a power, but the power I'm taking it to is the 1/3. So I throw another parentheses and do 1 divided by 3 because that's a third, and then I slam enter. So I raise this to the power of 1/3, 1 divided by 3. I hit enter, and I get 4212529.2, which let's just round that up or round that to whatever. I get about 4.2 times 10 to the, let's move my decimal over, 1, 2, 3, 4, 5, 6, 7, times 10 to the 7th meters. Okay, so this problem was really kind of solved for us. Much earlier, we kind of solved this problem all the way up here. Like that's where we had the answer, but actually crunching through those numbers was the hard part, but we eventually did it right here. So not too bad. Those are just two special orbits here on Earth, the geosynchronous and the geostationary orbit. We can solve for that orbital radii using Kepler's law, t squared equals 4 pi squared r cubed over gm, and just plugging in some numbers in seconds gives us our answer in meters. Okay. If you want to see how to kind of use Kepler's law without dealing with all these insane numbers, you want to get maybe g out of there, you want to get the 4 pi squared out of there, there's a special way to do that. We'll see that in the next video using what are known as solar Earth units. But for now, this is finished. Take it easy. Have a good one. Ta-da!